All right, we have another static equilibrium problem. I really like this problem. It's a good problem. What you have here, real good world example here, is we have a ladder leaning against a wall with some angle here, theta. The ladder is 3 meters long. We also know that this ladder, the coefficient of static friction between the floor and the ladder is 0.40. There's no friction between the wall and the ladder. So what we want to know is what's the minimum angle you can have here. So we want to make this angle as small as we can, but if we make it too small, the ladder's just going to fall. So if you've ever used a ladder, you realize that there's kind of a magic spot that you want it to lean a little bit, but you don't want to lean too much or the whole ladder will just slide out. We want to calculate what that minimum angle is by using static equilibrium. So what we have to do is draw our ladder and put all the forces acting on that ladder. Now, from the ground where it touches here, we're going to have a force coming up. We're going to call this a vertical force, or you could call it a normal force. Okay, I call it a vertical force because we're also going to have a force from the wall here, which I'm going to call the horizontal force. Both those are technically normal forces from the wall and from the floor. But I'm just going to call them a force vertical and force horizontal. Then the mass of the ladder is going to be mg going this way. And the thing that's keeping it from sliding here is the friction force that's going this way because the bottom of the ladder is trying to slide out like that. Alright, so what we need to do is try to figure out what this angle is. And that's going to be interesting because you notice that we have an angle here, this angle here, but what we need for this one is this angle. Well, those are not the same. This angle down here is theta. We'll call this one phi. They're they're complementary. So theta is equal to 90 minus phi, or you could do the other way. Phi is equal to 90 minus phi is equal to 90 minus theta. Because that angle is not the same as that angle, but together they make a right triangle. So they have to add up to 90 degrees. Alright, how are we going to do this? Well, we have to use our static equilibrium. Remember, static equilibrium says F net x equals 0, F net y equals 0, and the net torque is equal to 0. Okay. Now the net torque, remember, you can pick your rotation point. So where do you want it to rotate about? Well, I'm going to have it rotate about this point down here. We're going to call this our rotation point. Okay. Then we have torque from this one up here going this way. Okay. Notice this angle theta is the same as this angle theta up here because those are alternate interior angles of parallel lines. So what I'm going to do, and this force coming from the wall up here is trying to make it go clockwise, so this becomes minus the horizontal force times the distance, we're just going to call that L, times the sine of theta. That's the torque coming from the horizontal force. Now the torque coming from gravity is making it go the other way, so this becomes plus mg L over 2 because it's halfway up, and that's going to be the sine of phi. Okay, and this is equal to 0. Alright, so far so good. Now we can, I'm just going to rewrite this so we can see this a little better. This is minus FH times L. Sine of theta is equal to mg, well not equal to, I'm sorry, plus, it's a plus mg L over 2. Now the sine of phi we already got is sine of 90 minus theta because phi is equal to 90 minus theta. Well, if you remember from your trig identities, the sine of 90 minus theta is just equal to cosine of theta. And so I'm going to replace that with cosine theta so we don't have a complex part in here. And I'm going to move this to this side. So we got FH L sine of theta is equal to mg L over 2 cosine theta. Okay? Now I'm going to divide by cosine theta over here. I'm going to divide this so I get these by itself. So I'm going to have sine of theta over the cosine of theta is going to be equal to mg L over 2 over FH L. But the L's cancel, so this becomes tangent of theta, or sine over cosine, is equal to mg over 2 FH. And theta is equal to the inverse tangent of mg over 2FH. However, I don't know the mass and I don't know FH. So how do you solve that? Well, we got to go back and use one of these. Let's do F net x. F net x, we have a horizontal force, which is positive, minus the friction force, which is going the other way. This is equal to 0. So the horizontal force minus the friction force, which is mu sub s, times the normal force, but the normal force in this case is the vertical force. So far so good. So the horizontal force is equal to mu sub s times the vertical force. Well, now I got to figure out what the vertical force is. Well, I have to do F net y. F net y, I have mg going down, so it's minus mg, and positive vf, fv. So fv is just equal to mg. Then I plug that back into there, and I get that the horizontal force is equal to mu sub s mg. And then I plug that back in here for the horizontal force, and I get theta is equal to the inverse tangent of mg over 2 times mu sub s mg. Or those cancel out, and you get theta is equal to the inverse tangent of 1 over 2 mu sub s. And when you do that, you're going to get theta is equal to inverse tangent of 1 over 2 times 0.4. And let me grab my calculator here. And so the inverse tangent of 1 divided by 2 times 0.4 is equal to 51 degrees. And that is your answer. Alright, the reason I like this one, because this is one of the few equilibrium problems where you have to use F net x, F net y, and net torque to actually solve the angle. If the angle is 51 degrees, if that angle gets any less than 51 degrees, friction can't hold it and the ladder will slide away.